What's up guys, this is Matthew Burns and welcome to your tutorial on the memory unit for the 8-bit computer and the decoder we're going to be using to address individual bytes within this memory unit. I have the decoder sitting there on the floor. It is soldered to that Radio Shack board and I have it set up for a demonstration. First, I'd like to talk a little bit about the memory unit. I mentioned in the last tutorial that the memory unit was going to be 16 registers. All their inputs are connected. They have one set of input wires going to every single one of these boards because they're going to be connected as if they're one register. But I'm going to use a few control boards to be able to select one of these registers out of the 16 to use at any given time. This here is one of them. This controls the enables. Now, before I talk about what this is here, I have to talk about what these two chips are. These two chips are buffers. It's kind of, at first, when you first start looking these up or reading about them, you might think, well, that's a useless logic gate. It's an inverted inverter, basically. Yeah, I said that. It's basically a wire. But the difference between a buffer and a wire is the buffer has two enables. Well, this particular chip has two enables. It might just have one. And when the enable's triggered, the output will reflect whatever the input is. This has 8 different inputs, 8 different outputs, and each input corresponds to an output. And the enables are active low. So when both enables are pulled low, which I have them soldered low, I only need one enable for these chips. So I have one of the enables soldered low. I have the other enable attached to this wire here, which I'll pull low with something else in the computer that has to do with the control matrix. But when that happens, when both of these enables are pulled low, the output from the decoder will go through these buffers and output here to enable one of these registers whenever I want the memory unit to input data. Another thing about buffers, we're going to be using them on everything that dumps data onto the 8-bit bus of this computer. I'm also going to use them in other various locations when I see fit, but the reason for that is because they can drive more current than just like an AND gate could. You might say, well, why don't you just use an AND gate to control the flow of data? Because one particular application for the AND gate is that when you if you use one of its inputs as the input for data and the output as the output for data, and you use the other input as I guess the enable, when you pulse the enable high, the output will follow whatever the input is for the data. But an AND gate can't drive as much current as a buffer can, as this is their intended application. So that's exactly what these are. Their exact part number 74HC541N. It's an octal line driver. It has 8 bits and it's just a buffer, so it's nothing big. But I have all the enables of these 16 registers connected to the outputs of these buffers. I have one enable of each buffer soldered, pulled low, and I have the other one attached to this wire. They're both attached together. I'm treating these two buffers as one, because I need to control 16 wires instead of 8. So when I pulse this wire here low, what'll happen is whatever I feed to the inputs, which is not currently soldered to the board, the inputs are still hanging off of that board. You can see them over there. The outputs will reflect whatever the input is, and the way the decoder was designed, only one of the wires will be high at any given time. It depends on what the binary input is. I'll talk about that a little bit more later. So that's how I can select one enable at any given time. All the power and grounds are kind of self-explanatory. They'll just be hooked up to power and ground. The input wires are all the same. They don't need to be different because I can select one enable at any given time. And the output is a little bit more complicated, not conceptually, but there's a lot of wires to deal with. So I sent away for a board, same company that makes these boards here, pad to pad. I at first attempted to make the board, but I guess I was out of practice with making printed circuit boards, and I don't have any more photoresist printed circuit boards. So I had to send away for one. There are going to be 16 buffers on that board. Each of these wires, each data output from each register is going to go to the input of a buffer, and between the control matrix, which will send an active low signal to to one enable on each of the buffers, and the inverted signals from the decoder, which will pick a specific buffer to send an active low signal to. I can have one of these output data at any given time. So that's basically all that board does. I can talk about that more later. I'll draw up a complete schematic diagram of that when I actually get the board in, or I could do that sooner, but I just felt like recording before I actually went into that. I'll post that on my website at electroburns.com. So that's basically it for the memory unit. We went through how the registers work. I told you how I'd be connecting them in the last tutorial, and I went through it a little bit more now. So I guess I'm going to move on to the decoder. So the decoder is a device that has a 4-bit, in this case, binary input, and with four bits you have 16 different possible combinations, binary combinations for inputs. So I have 16 outputs there, and depending on what the input is, there'll only be one output. So it's actually easier to explain just by showing you than talking about it, so that's what I'm going to do. And then after that I'll go through how I designed and built the decoder. So first I'm going to supply power, and you'll see that the inputs I have pulled low through 1 kilo ohm resistors, and those wires there that are plugged in are just so I can pulse them high. Right now you see only the very last LED is on. Actually, I'm going to remove the camera from its stand once again. It's difficult to view that while the camera's at an angle. So right now, if you look at the inputs, they're all low. None of them are being pulsed high. And the output, only the last LED is on. So the binary value of 0, I guess, will have that far LED on the very end lit up. If I make the binary input value 0, 0, 0, 1, actually, give me a sec. These breadboards aren't very good, as power bus only goes halfway across. 0, 0, 0, 1, you'll notice the light switch to the second one, not the first one. If I change the binary value to 0, 0, 1, 0, the third one will be lit up. If I change it to 0, 0, 1, 1, the fourth one will be lit up. And so it'll go like this all the way up the LEDs. Each binary input corresponds to a different output. And so if I were to plug in all of these wires, 1, 1, 1, 1, you would expect the very last 16th LED to be lit up, which it is. So that's what the decoder does. It'll allow me to take a 4-bit binary input, which will be from the memory address register on the computer, we'll talk about that more later, or the actual user input with switches for programming, and it will select one register from the memory unit at any given time to access. So that is how we will communicate with 16 different registers and use one at any given time. In a minute, I forgot to bring my whiteboard with me, so I'm going to shut this camera off and go retrieve that. In a minute we are going to go over exactly how the decoder works, the logic diagram, and yeah, that's pretty much it. Alright, what's up guys, I'm back. And now we are going to be going over the logic diagram and how the decoder works. So, I don't know if you can tell right now, but what I've drawn at the top of this board, because I didn't want to draw it during this tutorial, are 16 AND gates with their outputs drawn. I don't have their inputs drawn. They're 4 input AND gates, and we're going to draw them as we build this decoder. Those are 4 inputs. Those 4 lines at the bottom are the 4 inputs that we're going to use to select one of the outputs. The outputs of the AND gates are the outputs that are going to be going to the memory unit. So, the first thing we're going to do is we are going to take each of these inputs here. We have 4 inputs at the bottom, and we are going to invert them so we get an inverted set of inputs as well. Sorry, drawing sideways is fairly difficult. There's 1. There's 2. There's 3. And there's 4. Perfect. Looks wonderful. I'm going to actually draw the inverted outputs in blue instead of black so we can keep track of what's what while we're designing this, building this. So, before I actually go and draw this all out, there are many different ways you could do a decoder. You could come up with some crazy logic diagram that will only have a high output when an exact code is sent in, use all different logic gates, and come up with something that is very heavy on how many chips you use, and works great, but is a little bit messy and tough to look at. But instead, it's much easier to use this established design, and I'll show you how this decoder works, and also I have to show you where I added the buffer. I added a buffer to this because I wasn't sure the inverters or whatever the input signal was would be able to drive that many inputs of AND gates, and so I also added a buffer in here. I'll show you where I put that when I finish designing this decoder, but for now we have 16 4-input AND gates across the top of the board. We have 4 inputs and 4 inverted inputs. So the first thing we're going to do is we're going to wire up the AND gates together, their inputs together. So starting from one side, we are going to wire an input to every other one. And you'll notice when we get to the end that the very last one will not have any wire connecting to it. Then what we're going to do is, starting from the far right side, we're going to wire every 2 together. I know those wires aren't jumping over each other, but I wasn't going to draw all those in. So then we wired those 2, we're skipping these 2. We're going to wire these 2 together. We're going to skip these 2. Wire these 2 together. Skip these 2. Last but not least, wire these 2 together. And again, you see we're going to skip the 2 on the end. Now what we're going to do is we're going to wire every 4 together. So this one, the first one, second, third, and fourth are going to be wired together. Then we're going to skip the 5th, 6th, 7th, and 8th, and wire together the 9th, 10th, 11th, and 12th. Now, last but not least, for this side of the decoder, we're going to wire together every 8. And so just the 8 on the right-hand side are going to be wired together. The ones on the left-hand side, I'll show you what we're going to do with those in a minute. So yeah, that is an input. I know that looks messy. 1, 2, 3, 4, 5, 6, 7, 8. Alright, so this is 1/2 of our decoder, and I'll go through exactly how it works. As soon as I finish drawing this up, it'll become fairly apparent, but for now, let me just finish drawing this up. So we're going to do the exact same thing we did from the right-hand side, but we're going to do that from the left-hand side instead. we're going to wire up every other AND gate. And so the first one, I'll wire this first one, or actually that's the 16th if we called that one, but whatever. The 3rd, 5th, 7th, 9th, 11th, 13th, and 15th. Now what we're going to do is we're going to wire every 2. So these first 2 are going to be wired together. We're going to skip the 3rd and the 4th and go right to the 5th and the 6th. We're going to skip the 7th and the 8th and go to the 9th and 10th, skip the 11th and 12th, and finish on the 13th and 14th. Next, just like we did on the right hand side, we are going to wire every 4th together. So, the 1st, the 2nd, the 3rd, and the 4th are going to connect to, not to the 5th, 6th, 7th, or 8th, but to the 9th, 10th, 11th, and 12th. 9, 10, 11. I know this is getting really messy. I'll include a completed schematic of this with the buffer and everything, probably on the same page that I post this video on, electroburns.com. And then, last but not least, just as we wired together the right hand side, we're going to wire together the 8 on the left. 1, 2, 3, 4, 5, 6, 7, 8. We don't need that. Alright, now we're to attach the inputs and the inverted inputs. So all the inputs we're going to attach to the 4 sets of connections on the right hand side. All the inverted inputs we're going to connect to the 4 sets of connections on the left hand side. But you'll notice each input corresponds to an inverted input. One of them is inverted from the other. So if I connect this first bit here, let's say, to the far right hand side connection, which is the connection that connects to every other, the 1st, 3rd, 5th, 7th, all the way up to 15th, then I'm going to connect this inverted input that corresponds with it to the, I will connect that inverted input to the one that alternates every other starting from 2, 2, 4, 6, 8, 10, 12, 14, 16, and that's this wire here on the far left. So the next bit, if these were every other, these bits here are going to be every 2. So the non-inverted second bit we're going to deal with is going to connect to the wire that connects every 2 for the AND gates. So that is this wire here. This wire is connected to the 1st, 2nd, not the 3rd, 4th, the 5th, 6th, the 9th, 10th, the 13th, and 14th AND gate. The inverted wire is then going to be connected to the one that jumps every 2, but starting from the left. So it'll be connected to the, I have to think about this, the 3rd, 4th, 7th, 8th, 11th, 12th, and the 15th and 16th AND gate. The 3rd bit here, as you can guess, will be connected to the bit that jumps every 4. It'll be connected to 1, 2, 3, 4, 9, 10, 11, and 12. The inverted AND gate will be connected to 5, 6, 7, 8, 13, 14, 15, and 16. And last but not least, the fourth bit is going to connect to the right 8 AND gates, and the left, and the inverted bit is going to connect to the left 8 AND gates. Well, I connected this wire to the wrong spot. I apologize for that. It's probably too messy to see anyways. Make more sense just listening, but I'll include a completed schematic, probably at the end of this video also, because this is pretty bad. I know. I have to apologize for that. It's really not as complicated as my drawing here is making it look. And so now that we have all these wired up, let's go through what will happen. So if I have 0, 0, 0, 0 on the inputs, only these left 4 wires, the inverted bits, will be high. And so only whatever's connected to 4 inverted wires is going to turn on. So if we start with this farthest left inverted bit here, this is connected to the left 8 AND gates. So by having a 0 here, we limited down our options to the 8 AND gates on the left. By having a 0 here, by having a 0 here, this wire here is also a 1. This is the wire that jumps every... oh man, this is messy. It jumps every 4. So it hits these 4 and another 4 over there. So we've limited our options for AND gate outputs from the 8 over here to the 4 over here. So just these left 4 are our possible options now. Now by having this inverted bit 1, because this is 0, having this third here inverted bit 1 actually, because this is 0, this is the bit that jumps every 2. So these 2 are selected, not the 3rd and 4th, the 5th and 6th are selected. So we've limited our selection from these 4 bits to just these 2 bits here. Now, having the 4th input be a 0, this inverted 4th input is a 1, and so we've this is the one that jumps every other starting from the far left. We've limited our option from these 2 to just this one. So you can run through examples like that. That's fairly easy to do. It's really not as complicated as it looks. Let's do one more. All we're doing with each bit, we're just limiting our selection more and more. And if you notice, each corresponding between an inverted bit and a non-inverted bit, it covers the input of every single AND gate. So each one cuts the selection in half. So let's try 0, 0, 1, 0. So another way that we could actually do this is, well, you know what, it would be simplest actually just to do this the way we were doing this before. So we know that this inverted bit, not this one, and this inverted bit are high, because they're just simply inverted from whatever these are. So let's look at what selection we have. We know that this inverted bit here will select one of these 8. That is the inverted bit that goes to the 8 far left inputs. This inverted bit here will select one of these 4 AND gates or one of these 4. But because it's one of these 8, we've just cut our selection in half to one of these 4 AND gates here. This 1 here will actually go to this one. This 1 here connects to every second AND gate starting from the right. So we'll hit these 2, these 2, these 2, and these 2. So of the 4 that we had selected, our options are now either this AND gate with the dot in it there, or this AND gate with the dot in it there. Our selection is of one of those 2. Now the last bit that we have to look at is, again, the 0 on the far right. The 0 on the far right will have an input signal on every other, so it'll have an input signal on this one and this one, but not this one. So of the 2 we have selected, we've narrowed down our decoder selection to the left of the two bits, and that is what 0010 will light up. 0010 is the third possible combination, because 0000, 0001, 0010, and as you can see, it is the third input from the left. 0000 resulted in the first one. So you can probably guess that each input will move the output 1 to the right, and that you would be correct. If we had a value of 1111 on our inputs, which I just erased, you can see that the only AND gate, another way to do this, the only AND gate with 4 black wire inputs, the way they're drawn, is the one on the far right, and so that's the one that will light up. So that's basically how the decoder works. It's not a very complicated device. It just looks really complicated the way I drew it, because I have terrible handwriting, drawing, whatever. Yeah, that's the other thing I was going to remind you about. I was going to talk about the buffer. There's really not much to talk about here. I already went through what a buffer was earlier in this tutorial, but basically, I'm going to draw a buffer here. I placed a buffer right at this point. Forget the circuit diagram symbol. I'm just drawing a box. Placed a buffer right here because I was not sure how much current whatever logic gates were supplying the input from the memory address register, or what the inverters could handle. I wasn't sure how many AND gates they could supply current to before too much current was being drawn. So I just placed a buffer in there, and that's pretty much it. It doesn't change the schematic in any way, and that is how I built my decoder. I promise you guys I will include a really neat looking circuit diagram in pencil, not in dry erase expo marker, and I'll post that on my website at electroburns.com, the same place I post this video. So thanks for watching, and in the next tutorial I'm probably going to jump to something different because I'm waiting for the board for the output of my memory unit to come in. And so I'm probably going to work on the program counter. I'm actually going to talk about that just for a minute now. So what the program counter is, I don't think I've went over that yet in this tutorial. We don't need this. The program counter is the device that stores what current memory location for running code that we're in. We have 16 bytes of memory. That's the memory unit I just discussed in this tutorial and I just showed you. Well, that memory location is going to be used to... We don't have any other memory in this computer. That memory location is going to store, I guess you could call them variables, though we're not going to have a name for them. We're just going to know it's a value in a location. It's going to store, so whatever data we want to store, it'll store the data. Whatever code we want to run, it'll store the code. In ones and zeros, of course, machine code. But that memory unit holds everything this computer has. So we're going to start writing code on this computer, probably at the first location, 00. Well, the program counter, so once I execute that piece of code, what does the computer do? Well, how does it know to jump from 00 to 0001 and start running the code at the next location? And then when it finishes the code at that location, how does it know to jump to the next piece of code at the next location? Well, that is the job of the program counter. That's what the program counter is going to do. I'm not going to go into how the program counter works in this tutorial. That is not in the scope of this tutorial. That will be the next tutorial. But I will tell you now, if you know anything about program counters, I am not going to cascade a bunch of toggle flip-flops and just have each consecutive bit flip with half the frequency of the previous bit to make my program counter, because although doable, and I thought of some ways I could make this work, it's kind of complicated and messy to look at when I try to... I'm going to implement the jump command in this computer, and when writing a 4-bit binary value to the program counter to a bunch of cascaded toggle flip-flops is kind of a messy task. So instead, the program counter is going to be a register, just like any other register, except it'll be a 4-bit register. And just like the ALU we talked about at the very beginning of this series, for addition, we're going to make another 4-bit ALU. and the 4-bit ALU, the B input, will not be a register. It'll just be hardwired to 0001. And each time we increment the program counter to move to the next memory location and run the next piece of code, we're simply just going to be storing in the program counter what its previous value was plus 1. So that's pretty much it, how I'm going to make the program counter. That wasn't really part of this tutorial, I just wanted to talk about that for a while. So that's what I'll be working on. When I finish soldering that, I'll show you guys and I'll document it. So thanks for watching, and I'll see you guys next time.